All right, thank you. Thanks a lot for the opportunity to speak. So let me give you like a brief outline of what I want to talk about, and then I'll give some details later. So if X is a Calabrese threefold, then we can attach to this what are called the Donaldson-Thomas invariants of X. And these are invariants that have, these are numbers that have something to do with like curves inside of X. And a fairly natural question to ask is, if you care about these invariants, is, you know, if I modify X slightly, how do these invariants modify? So the basic question I want to ask is if X and Y are birational, sorry, if X and X prime are birational, then is there a relationship between the deta invariants of X and the deta invariants of X prime? So this is the question. Okay, so the answer is yes. So okay, there is a relationship. So answer is yes, and so the relevant names here are Huan Lee, Toda, myself, and then there's a recent preprint by Jiang where he generalizes this to DM stacks. And I just want to say a brief thing about the methods. So how do you prove this? Well, you need to use a little bit of derived categories and these things called motivic Hall algebras, which is sort of the fun part of the theory. And the relevant names here are, I should say, Bridgeland, Joyce Song, and Kuntsevich and Soywoman. Oh. Okay. And if time permits, I'll talk about an extension of this where instead of X prime being an ordinary variety, it's allowed to be an orbifold under the, and this goes under the name of the Kreppmann resolution conjecture, which is still open. So there's Brian Cadman Young is the paper where they posed this question. I had something to say about this. And then there's Dusty Ross actually proved the conjecture for in the toric case. Okay, but time doesn't usually permit. Okay, so this is sort of what I want to talk about. So let me give some details. So first of all, okay, what does X want to be? So X for me, X will be a smooth projective variety for the complex numbers. And X is a Calabrese threefold, so this means the dimension of X is 3. The canonical bundle of X is trivial. And I also want to require that H1 of X with coefficients in O is 0. Okay? Okay, so now I want to tell you what these Donaldson-Thomas invariants are. And I won't do justice to the theory. So there's at least two ways of sort of trying and explaining what these things are. One is to go back to the original thesis of Richard Thomas. And so he was interested in like giving some kind of sheaf counting invariants. And so you should be looking at like moduli space of stable sheaves. Then you should study the deformation theory of these. And then produce a virtual class, then realize that because of the Calabrese 3 condition, this virtual class is a zero cycle. You can take the degree of this virtual class and you spit out a number. But there's very deep work of Barrand, which gives you a different interpretation of these invariants in terms of like Euler characteristics. So I want to give you this sort of easier way of understanding these. Okay, so, right. So one thing we can attach to X is its Hilbert scheme. Well, let me fix beta a curve class, an X and an integer n. Then I can look at the Hilbert scheme. And what is this? This is the space parameterizing curves that sit inside of X. So these are closed subschemes of dimension at most 1 inside of X, such that C is of class beta n. Okay? I should have done this first, I guess. I'm stuck. Okay. Success. Okay. So, okay, more rigorously, let me say this differently. So since we're doing algebraic geometry, instead of looking at the spaces, I can look at the sheaves. And so this is the same thing as the space of quotients. And this point of view is not just, it's very important for what I'm going to say later. So I'm looking at quotients of the structure sheaf, and such that the Chern character of O of C is 0, 0, beta n. Okay? And the unhelpful picture is the following. So if this is x, then I'm looking at curves inside of x, and so, but I'm not imposing anything about the curve, right? So these curves could be singular, they could have multiple components, but even worse, they could have non-reduced components. So you could have a bunch of nilpotents. Even better, you could also have floating points floating around. You could have embedded points. So it's, this thing is really a mess. It's not, it's really parameterizing any subscheme of dimension 1 inside of X. This is in contrast to like Gromov-Witten theory, where the curves are really, really nice because they're almost smooth. So we have this modular space over here. And the naive thing we can do is the following. So we'll define naive DT invariant of X, class beta n, to just be the topological Euler characteristic of this space. Right? So it's definitely a number I can attach to the space, and it has to do with the curves inside of X. And formally, I'll just say that dt of X is this generating series of all the dt numbers. Where this is some formal variable. Okay? Okay, let me use this one first. All right? So to get the actual DT invariance, well, we need to use this work of Berend. And then I won't do justice to the work, but let me just mention that basically vaguely what is going on. So Berend, for any m over the complex numbers, he defines a constructible function nu from m to z. And using this, he defines this weighted Euler characteristic of m, which is given by the sum So basically, you take each stratum where this function is constant, and you take the topological order characteristic of it, and you weigh it by the value of the function. And just to mention a few properties of this, let's see. So that was a bad idea, wasn't it? Okay, much better. So the key property of that thing is that it, in contrast to the topological Euler characteristic, it can see nilpotents. So if I take the fat point, this guy, to be the dual numbers, then the topological Euler characteristic of this thing will be 1, because topology is just a point, which is different from 2, which is the chi-baryon of this guy. Because somehow what this thing is doing is that it remembers the fact that there's 2 points that are colliding together. The 2 points coming together to form a fat point. This guy doesn't remember this, but this one does. Okay. So of course I'm not telling you how this thing is defined, which is of course it's very deep and hard, but it's sort of better than this naive definition. And the other thing is that if M is smooth, then this thing is basically just the Euler characteristic. Okay. The results I'm going to talk about actually also hold for the naive DT invariant. So if you're more interested in this definition, this relationship under birational transformations is still valid. Okay. Let me try and use this one again. Oh, what? Yeah. So, so this is, as I was saying. So when you take the, I mean, you can make this definition whenever you want. That doesn't matter. But for it to coincide with Thomas's original definition, you need the Calabrese condition. Okay. So okay, let me see. Oh, and the other thing I want to say is that these Donaldson-Thomas invariants are deeply connected with like Gromov-Witten invariants, which is very surprising because so they're both. I mean, with the definition I've given, they're both like curve counting theories. So they care about curves inside of X. But here, right? So the curves are really horrible. There's no control over how bad the curves can be. But the maps are really nice because they're just embeddings. And Gromov-Witten theory instead, the curves are, let's say, basically smooth. They're really, really nice. They're not smooth, but they're very nice. But the maps they're not perfect because they're these stable maps, which have automorphisms and can collapse components. And it's striking that there's a relationship between the two. So there was these two very influential papers, these MNOP papers by Maulik, Nekrasov, Onkukov, and Pandaripande, where they conjectured that, first of all, so if you fix beta and you look at that as a function just of n, then this should be the expansion of a rational function, which is invariant under Q goes to Q inverse. And this was proved by Toda and Bridgeland independently. And not only this, so you take this rational function, you perform a funny change of variables, and you get the Gromov-Witten theory of X. And I think that the relevant names here are, so this is, as far as I understand, this hasn't been proved in full generality, but there's, but it's known in many cases, and the relevant names here are, so Maulik, Oblonkov, Okunkov, and Pandaripande, and then there's 2 papers by Pandaripande and Pixton. Right, okay. So, Pixton. Yeah. Which is, it's super surprising. I mean, I guess there was some string theory motivation, but I don't know if you, yeah. Okay. So I'll assume that now we're super interested in these Donaldson-Thomas invariants. And so this is a perfectly natural question at this point, right? So if I have 2 birational Calabrese threefolds and I want to compare these DT invariants, this generating series for DT invariants. And so first of all, there's the very general theorem of Kalamata, which implies that actually, so if X and X prime are birational, then there exists a finite chain of flops. Well, it's like connecting them. Okay. So basically, I'm saying I have this very general problem of any 2 birational Calabrese threefolds. I can break it up into the case of flops. And then morally, if I just tell you what happens for flops, and in theory, you can just recover whatever happens for an arbitrary birational transformation up to like knowing how explicitly how this is broken down into flops. So let me remind you what a flop is. Okay, so it's a special kind of birational transformation, and again the picture, which is I guess more helpful than that picture to draw, is this one. So you have so I have a y, which is my Calabrese threefold, and I have a curve c instead of y, so c will be a p1. And I'm contracting this p1 down to a point, which is a singular point of some guy x. So I kind of changed notation. So I want to compute the determinants of y now. So I'm contracting down this curve, and I have another Calabrese threefold w with a map g, which is contracting down a different curve, c prime. They're both p1s, but they're embedded in very different ways. Okay. Okay. So what makes a diagram like this a flop? Well, okay, so the point is that if I remove this curve and I remove this curve, y and w are the same. So up to this codimension 2 thing, they're the same. So I now can identify divisors. And so whenever I take a divisor here that was intersecting the curve positively, and I bring it over to the other side, then it now has to intersect the curve negatively. So there's this change of signs. And the theorem actually doesn't need to, I mean, you don't need to specialize to this case where just you have only one curve contracting. I mean, this, as long as X has isolated singularities, and you can have whatever you want for the fibers as long as like a chain of P1s, and the formula that I'm going to write down in a second still holds. Okay? I mean, there's a different perspective using derived categories, which is really what I need to prove this theorem, but sort of this is the geometric picture. Okay, so whenever I have, oh yeah, I should say this. So,
is the contracted point always non-smooth?
What? Sorry?
Is the contracted point always singular?
Yes. So I should say, so this thing, right? So I can identify divisors. So let me call the flop map. Let me call it something like phi. So I can identify divisors, and dually I can identify curve classes. So if I have my formal variable q to the beta n, I can send it to q to the phi lower star beta comma n. So this is my identification, which is dual to the identification between divisors, right? So again, what do we want to do? We want to say something about these curve counting invariants, and we want to say how they behave under birational transformations. Thanks to Kalamata, I can break down the problem into the case of flops. And in this case, I'm trying to see what are the special features here. And one of the special features is that I can really identify these divisors. And so now it really makes sense to compare the invariants on the two sides. And so I just want to say that something like this makes sense. Okay? Okay? And so the theorem is the following. And so again, Hohenli proved the special case using like degeneration techniques. Toda gave a proof using a different method, and then I gave the proof that I'm going to talk about. And then, as I mentioned earlier, there's an extension by Jiang. It's recent. So the theorem is the following: that there's a quantity which is preserved under a flop. So basically, I'm saying that this product here it doesn't change under the flop. After I apply this operator here, it will be sent to the same thing. So what is this guy? So let me define this. So recall the DT invariance of x, or in this case y, were sums over beta and n of what? Of this DT number, class beta and n, times this formal variable. So now, this x here stands for exceptional locus, and then the exceptional locus of any birational map is a locus where it's not an isomorphism. So it's a thing that has to do with all the curves that are contracted. So how do I impose this? I'm just saying, I'm just only summing over the curves that are sent to 0 under the push forward in homology. And this funny dual thing is just a change in signs here. And sometimes like the duality functor is responsible for this change in signs. Okay, so are there any questions? So this is the theorem I want to tell you about, which is saying that this quantity here is preserved under a flop. Okay. Yep. I don't know what to do. Okay. I'll just use this. Okay. So, in some sense, I mean, sort of why this theorem is true is sort of fun. So, yeah, how do you go about proving something like this, right? So, the first ingredient is this theorem of Bridgeland, which tells us that there's a relationship between the derived categories of y and w. So the Hilbert scheme has to do with like subschemes, but I express it in terms of like quotients of the structure sheaf. So it's sometimes you can view it as something about sheaves. So, I mean, this result of Bridgeland is going to turn out to be crucial. Right? So there's an equivalence between the derived category of y and the derived category of w. Okay. I should say, okay, by this I really mean the bounded coherent derived category of y, which basically just means take chain complexes of coherent sheaves. I'm identifying any coherent sheaf with any of its resolutions. So I don't need to tell you what this is, but I want to emphasize one like property of these kind of categories, these triangulated categories. And which is the following. So in these kind of categories, you don't have short exact sequences anymore, but you have these exact triangles. And as you probably all know, so whenever I have one of these exact triangles, then this will induce a long exact sequence in cohomology, and so on. And this will turn out to be crucial in a second. I know everyone knows this, but somehow it's kind of important. So an object in there is a chain complex. So it has cohomology, and an exact triangle will induce a long exact sequence in cohomology. So that theorem of Bridgeland is not enough, but fortunately he proves way more than that. So, and then this is where this thing sort of comes in. So actually he proves, so so again, the equivalence, so let me call phi this equivalence between d of y and d of w. So first of all, one thing that is useful for us is that it sends the structure sheaf to the structure sheaf. But more importantly, using too much board space. Can I do this? Oh, okay. More importantly, there's a special subcategory inside of this which is preserved. So inside of here, so there's a special subcategory which he calls the category of perverse coherent sheaves. Which is something which depends on this contraction here. And this is preserved under this equivalence. And this will turn out to be the really crucial thing. So let me define this category for you, which is really, it's really simple to define, so you might as well do it. Yeah. So naively, you might ask, where do coherent sheaves go under this equivalence? And I don't think this is clear. So if you ever work with this stuff, it's immediately obvious that coherent sheaves of Y cannot go to coherent sheaves on W, because if they did, then Y and W would be isomorphic already. So that's never going to happen. But somehow there are these other two categories, which are hearts of T structures inside these two categories that do match up. And how do you define these categories? Well, these are going to be like tilts at a torsion pair. So let me tell you what this means. So there's two subcategories inside of these, inside of coherent sheaves in Y. One is given by all the coherent sheaves such that R1 of F lower star of T is 0. And the other one is given as the F's such that F lower star is 0. Okay? So from this, it's immediate that the support of F is completely contained in the exceptional locus of F. So basically, this category here is only interested in what's happening, on things that on the locus which is contracted under this under F. And so what I do now is that you define this category here as being the tilt. So these are all complexes in D of Y such that this is 0 for I different from -1 and 0. H minus 1 of E belongs to F, and H0 of E belongs to T. Okay? So again, so the H minus 1 bit so these are two-term complexes, and the H minus 1 bit has to do, is all supported on this exceptional locus. Okay? So for example, I should have said this. So, so the structure sheaf lives in here. Any quotient of the structure sheaf lives in here, so any subscheme, and the structure sheaf of any subscheme will live in here. Things that live in here, so let's say the curve is C, so things like OC minus 2, OC minus 3, et cetera, all live in here. But they will not live in here. Okay, so this is basically the difference. And I'm slightly lying in the sense that there's actually two versions of this category that we care about. So if you notice here, there's no way this can form a torsion pair because like OC minus 1 can live in both categories. So, and then this being a torsion pair means that I'm taking this category here and I'm splitting it into two pieces, and they can't really, they don't talk to each other, right? So they have to intersect only in the 0 object. And basically, the choice of working in one version of the other is the choice of where OC minus 1 goes. And Bridgeland's theorem is actually that one version gets sent to the other and vice versa. So these two versions are swapped. So I need to add like an extra condition just to decide whether OC minus 1 is in here or in here. Okay? So this key property of being a torsion pair is a thing that actually given, so for A in a coherent sheaf, then there exists a unique short exact sequence like this. Where T is in T and F is in F. Right? And this is the same that The same thing happens with like if you have like a finally generated abelian group and you look at torsion groups and then torsion-free groups, and any, you take a group, you take all its torsion, kill it, and then you get a free thing. And this is the same thing, I mean, the same principle, but in this geometric situation. Okay. So now at this point, right, okay, so how are we going to use this? Well, we can mimic the definition of a Hilbert scheme, but with this category over here. So I'll define a Hilbert scheme in this category to be, so I told you that O of y lived in T, so in particular lives in this category. So I can look at surjections like this, where E is now in this category here, and S is surjective. Well, let's say epimorphism, if you want, inside of here. And now it follows immediately from the fact that I have an equivalence that that these two things will match up under a Bridgeland's equivalence. Right? So if the P weren't there, I'd be super happy. Because I could get rid of this factor, and it will tell you the DT invariants on one side are the same as the DT invariants on the other side. So, yeah. So basically what I need to do now is to relate these, or this P Hilb with the ordinary Hilb. And so this is why I brought up the fact that, any exact triangle will lead to a long exact sequence. Well, because we'll see it here, right? So if you give me something like this, so this is an exact triangle with I and E living in this category, which is the same as saying that this is a surjection in this category. I can look at the long exact sequence. So this is 0 because this is just a sheaf. Right. So I can look at the long exact sequence. So okay, this is telling me that this is 0. That's fine. So so this is saying that any perverse ideal sheaf is a sheaf. Okay. But really, the sort of naively, what's happening here is that if I'm given a surjection here, I can associate a surjection of ordinary coherent sheaves just by looking at what happens in cohomology, right? And so morally, and again, since any quotient of this guy lived in the category T, this is morally surjective. I can reach any surjection here of ordinary coherent sheaves. So I have a map, morally I have a surjective map like this. And let's say, let's call F the fiber. So if this were a fibration, let's pretend, then what I would have is that the topological Euler characteristic of the total space will be the same as the topological Euler characteristic of Hilb times the topological Euler characteristic of the fiber, right? And this is what is giving me my DT invariant. And what is this? So this has to do with the fibers. So the fibers morally have to do with this piece over here, which is H minus 1 of E. And this piece over here, so anything in F, the support was in the exceptional locus. So it's sort of intuitive that somehow the fibers have to do with like DT of the exceptional locus. Well, what? This is not is a complaint that this is not a proof. This is not the proof. I mean, this is sort of the idea. Yeah. I mean, yeah, this is sort of a pretend proof. To actually make this rigorous, you need these motivic Hall algebras. Yeah, let me leave this here. Okay, are there any questions? So again, so what's happening here? So we want to compare these DT invariants on the two sides of the flop. So DT invariants of Y and DT invariants of W. there's this equivalence of Bridgeland, which tells you that these categories of sheaves are the same. And actually, even more, there are these like two abelian categories sitting inside of it, inside of these categories that get identified. And using this, I have this kind of funny version of the Hilbert scheme, which gets identified. So now the point is to extract some information about the Euler characteristic of this thing. Yeah. Yep. Okay, so let me tell you a little bit about these Hall algebras, which is the way to formalize this, this thing that I just said. Okay. So, right. So there's this thing called the Grothendieck ring of varieties. And this is the free abelian group spanned by isoclasses of varieties, modular relation, and then the relation is that if y is a closed subscheme of x, then the class of x is the same as the class of y plus the class of x minus y. And this is a very interesting ring. There's many open questions about this, but somehow we don't need, we're not going to need anything deep about it, but just this flexibility of being able to chop up like a variety into these like, into the sum of, if you have a stratification of x, I want to say that x is the sum of all its strata. Okay? So I can do something slightly fancier, which is if I fix a base, I can work with like varieties over the base S. And so instead of taking just varieties, I can look at maps like this. And the equivalence relation will be the same. Whenever I have a closed subscheme, then I'll have this. Okay, so I'm just doing everything, like adding this S thing here. Okay. Okay, now suppose that we have a diagram like this. So let's say I have some guy T with a map to S cross S and another map to S. Then this having a diagram like this will enable me to define a product on this Grothendieck ring. So let's see, if I have two classes like this, then I can consider the map from X cross Y into S cross S. I can take the fiber product, and then I can take this composition over here, and I'll call this F star G. Right. So far it was formal. But now I want to apply it in some examples. So
what was T?
A T is anything. I'm just saying if you have a diagram like this, then you can do something like this. It's just a general fact of life. So, but now I'm going to tell you when it's actually useful. So if I take S to be the space of all coherent sheaves, well, the stack of all coherent sheaves on Y, and T, I'll take the stack of exact sequences on Y, then this is actually useful now. Oh, I ran out of space. Okay, let me write it here. And the map I'll be considering is the following. So if I have a short exact sequence like this, I can send this one to A comma C, and I can send the short exact sequence to B here. So this is the space that's parameterizing all short exact sequences of sheaves on Y. And this is the space that's parameterizing all sheaves on Y. And whenever I have a short exact sequence, I can just forget the middle term, or I can remember just the middle term. And this is the diagram I want to consider. And somehow this thing works, because it's remembering things about this abelian structure, right? It's remembering things like extensions, and so therefore surjections and similar things. So let me make this more precise. So, okay, so let me say what this whole algebra should be. So, okay. So I'm going to take this Grothendieck ring. Well, yeah. Now this is tricky because it's not clear what I should. There are different versions of this algebra. But let me be super naive and just say I'm just going to take like stacks over this guy, and then I'm going to endow with this. Well, not that board, of course. Yeah, that thing. Okay, and this is the Hall algebra. Yeah, I've covered this, haven't I? The thing is over here, okay? Right. So all I'm saying is that I take this Grothendieck ring, which is the thing that lets me chop up varieties really lets me use stratifications. And then I'm using this setup over here. So the product is really knows something about extensions, right? So because I mean, if you think about it, a map from let's say X to S. So S is now the space of all coherent sheaves on Y. A map from yeah, Y was unfortunate. Let's say X. So this is a family parameterized of X of sheaves on Y. And when I do this funny thing, I'm basically remembering all extensions between the two families I start with. But let me give you like a concrete example, which is probably more useful. So in this huge algebra, I have some elements. So one element is this guy, which is defined to be the identity. Okay. I have another guy which is similar. So let me consider the stack, which is parameterizing maps from the structure sheaf to some sheaf. And I take the thing which is, let me write it this way, which is forgetting. Okay, so I have some space which is parameterizing a sheaf and a section, and I'm just forgetting about the section, and then this is the map that is giving me the element in the whole algebra. Is that clear? There's also another map which is basically the Hilbert scheme, which does the same thing. So a Hilbert scheme is a sheaf plus a surjection from the structure sheaf, and just forget the surjection, and I get a map here. Okay, so now the claim is that the first isomorphism theorem gives me a really nice identity in this algebra. right? So this one O co-element is actually the product of H, the Hilbert scheme, times this. And why is this not surprising? Well, let's think about this. So this guy corresponded to things like this. So this corresponds to a modular space parameterizing O and then a map to some sheaf. But whenever I have something like this, I can always factor it into a surjection just by taking the image. And then I can take the co-kernel. Right? And what is this guy? This is parameterizing short exact sequences where the outer two terms, one has a surjection from O, and the other one is just some sheaf. And vice versa, if I start from something like this, I'll be able to get, like by composition, I'll be able to get a map to E. And this is sort of the fun part of this subject, is that there's this huge algebra, but somehow it remembers these basic things about this abelian category, like the first isomorphism theorem. So another useful thing is that, so again, I have an object, I have an element 1t, which is given by, so you have to prove it, but yeah, there's some space parameterizing all objects in there, and that sits inside the stack of all coherent sheaves. And I can do a similar thing with 1f. And because this was a torsion pair, it's not surprising that I have this identity over here. Right? Because any coherent sheaf can be split into something torsion. I can kill the torsion and get something torsion-free. Right? It's exactly this thing over here. So, yeah. So, okay, this has to do with the Hilbert scheme, and so eventually it will have to do with like these DT invariants. And I'm able to, and I have this identity over there, which might be useful. Then I have this other identity. Oh, maybe I should, okay, well, yeah. And the other identity, which is, oh, sorry, let me do it there. The other identity that I have is the following. So I can do a version of this O element even with these categories. So I'll have something like 1TO, which is, so again, this is the stack parameterizing a guy in T with a section, and then I just forget the section. Okay? And again, from the definition there, then it's clear that these sheaves here don't have any sections. And so what turns out, yeah, you can check that then you'll have the following identity. And so using this, I can deduce the following. So I have 1TO times, yeah, sorry. Well, let me say 1TO, 1 over F is equal to H, 1T times 1 over 1 sub F. And now let's pretend that these are invertible elements in the Sol algebra, which is in a suitable sense they are. Then I can actually cancel these two, and then I'll get a nice description of H in terms of just this T category. But the nice thing about this T category is that it really sat inside this perverse category. And so now it's getting closer to the point where I can actually use it to relate this H with the corresponding guy in the perverse setting. Okay. let me do that. All right. Right, so at this point, I can do exactly the same things, but instead of taking the Hall algebra of this guy, I can take the Hall algebra of this other category, this Bridgeland category of perverse coherent sheaves. Has exactly the same definition, but instead of having co here, I have to like write per, but everything goes through. I mean, it's kind of painful to work out all the details, but it's fine. So, and again, I'll have something very similar. So I'll have, so I have my element pH, which is the perverse Hilbert scheme going to this guy. And I have my first isomorphism theorem. Yep. And now I can use the fact that I have a torsion pair. So yeah, whenever you have a torsion pair on your category co, you do this tilt thing where you define this category of perverse coherent sheaves as I wrote down earlier, and then you inherit a torsion pair there. Only one of the factors is shifted. So this is basically, it's still the same torsion pair, but it's sort of shifted. And this guy will have a similar thing. Right? And so now we can use that identity. Right? And now at this point, I can, again, cancel these two factors. So sorry, this was a t. OK. So now I'm done, right? Because I've related this guy to this guy. And now there are two things that I need to tell you, and then somehow I won't really justify them. So one is that, so then I need to take care of this other factor over here. And it turns out that by applying the duality functor, so Helms in the structure sheaf, I actually can relate this thing to some version of H of the Hilbert scheme that has to do with things that are only supported on the exceptional locus. Okay? And the other thing that I'm not telling you is this integration morphism, which is a huge part of the theory. Because, I mean, at this point, okay, let's say I proved something of the form HP is equal to H star some other element, which has to do with like the Hilbert scheme of things that are supporting the exceptional locus. We still don't know, we still don't know what, this is some identity in some random algebra. It's not clear how this relates to the actual DT invariance. Where it turns out there's this map. Well, let me just say it naively. This integration map. And this is possibly one of the most subtle points of the theory, and definitely not doing justice to it. So this is, well, let me just call it some ring R, which is basically the ring of the ring of these generating series. Okay, and the idea is basically if M is a variety, so no automorphisms, then this thing. So let's say, yeah, okay. Let me be, since I still have a little bit of time, let me be a little bit more precise. So this thing here, the stack of perverse coherent sheaves. Oh, actually, let me just do it for the coherent sheaves, which is way easier. Okay, so this thing over here, this splits as a disjoint union according to the Chern character. So this thing is, so these are the coherent sheaves such that the Chern character of F is alpha. Okay? And now this thing is defined so that the following holds. If M is a variety, okay, so again, no automorphisms, then I of m mapping to, let's assume this factors through co of alpha. Then this thing is sent to, well, basically the chi-barand of m times q to the alpha. So given the existence of this integration map, I mean, I'm done, right? Because I then can apply this integration map, and then I'll have that this thing, which is taking the, this thing will go to these Euler characteristics of this perverse Hilbert scheme guy, but this will go to the DT invariants. So I have something like, if I look at the Hilbert scheme, but now supported only on curves, this gives me precisely the DT invariance of y. Yeah, but of course, I'm hiding many details here because the construction of that is very subtle and somehow, yeah, I mean, the fact that you should be restricting to curve classes is really essential. Yeah, sorry, let me stop here.